Hi, my name is Luc Lenain. Today I'll be talking about the contribution of high-frequency wind-generated surface wave to the Stokes drift. This is some work that I did with Nick Pizzo. We are both from the Scripps Institution of Oceanography in UCSD. I should point out that this work was recently published in the Journal of Physical Oceanography, and you have some information about this at the bottom of the screen. And I highly recommend that you take a look if this is of interest. Today's presentation is really a brief summary of the work that we conducted as part of this project, and there's a lot more to it. The main idea here is to use airborne observation of surface topographies that we collected using an aircraft. This is one of the flight over 3 experiments off the coast of California. And from those topographic measurements of surface wave, and in particular wind-generated surface wave, the idea is to parameterize the properties of the surface wave field across the so-called equilibrium and saturation ranges. And I'll go over some background on this in a second, because this is of significant importance to wave modeling. And once we have this better depiction of the spectral shape of wind-generated wave, we took it a step further, looking at the Stokes drift, and in particular the contribution of high-frequency wind-generated waves to the Stokes drift, as well as the impact of an incorrect parameterization of this transition to the Stokes drift, because this is a crucial importance to couple RC modeling. This is how, through the Stokes drift that you set the boundary condition for those models. So, before I get into those results, I wanted to give a little bit of background on surface wave and wind wave simulation. So the theoretical foundation of wave generation by wind were established in the 50s by Miles and Phillips and others, as well as nonlinear wave-wave interaction in the 60s, again by Philip Sesselman and Zakharov. The basic behind wind wave simulation is to generally represent this process through the radiative transfer equation, and that's what I'm showing here. On the left side, you have the wave action, and on the other side, you have a series of source terms, 3 primary source terms, which are energy density source terms. So you have the wind input, that's really the wave grows due to the wind, nonlinear wave-wave interaction, and the dissipation, which is primarily due to wave breaking. So how do we go from this to a spectrum, to a wave spectrum? Well, Phillips in 1985 considers the existence of an equilibrium range where where you assume that the nonlinear energy flux, wind forcing, and energy dissipation are in balance, proportional, and of similar magnitude. So by making those assumptions about an equilibrium range, it leads to a directional wave number spectrum in the equilibrium range of this form, with the -7/2 power law in the directional form. To make it a little simpler, if you azimuthally integrate this directional spectrum, you obtain an omnidirectional spectrum, and I'll be talking a lot about this today, which has a -5/2 power law. So this is, our understanding of the equilibrium range. For higher frequency wave, beyond the equilibrium range, we find the saturation range, where the primary balance is between wind forcing and energy dissipation. As the nonlinear energy flux gets much smaller, that leads to a different shape of the directional spectra. This time it's a k to the -4. K is the wave number, obviously. If you azimuthally integrate this directional spectra, you get another directional spectra with this time a power law of -3. So this is our understanding of this transition between equilibrium and saturation range. This is our understanding of the spectral shape of wind-generated wave. Observational evidence of this transition is very challenging to obtain because of the broad range of frequencies that we have to be able to resolve with one instrument, and that has motivated this work. As I mentioned, we're using observation here. So we're considering 3 experiments, all funded through the Office of Naval Research, First one is a SoCal 2013. This is San Diego here, Catalina Island, San Nicolas Island, and San Clemente Island, kind of like in between here. This was also the location of the Langmuir DRI, LCDRI in 2017. And I'm also using data from the inner shell DRI, kind of like the deeper site. There's a lot of data collection close to shore, but when they're not considered here, we're only looking at the deeper data. Overall, we had a range of wind speed in the 2 to 13 meters per second and significant wave height of up to 4 meters. So it's a pretty nice set of observation covering a broad range of environmental conditions. To collect sea surface topography measurements, we are using the modular aerial sensing system that we also call MASS. This instrument has been developed by our group for almost 10 years now. We actually have 2 instruments in operation now. We've flown the system extensively for a broad range of topics. It's been really a workhorse for us. At the heart of the MASS, you find the scanning waveform LiDAR from Rigo that is capable of measuring surface wave, surface slope, and directional wave spectrum with great accuracy. What I'm showing here on the left is a 3D point cloud color-coded for height. This was some of our first flights here, and this was just flying on top of a platform in the Gulf of Mexico that I'll talk about a little later on. Conditions were about 12 meters per second wind, 3.1 meter significant wave height, a lot of short waves with spatial resolution, and I think it gives you an idea of the resolution. You also notice those points here, which are not outliers. Actually, they are birds, and I think it's another testimony of the accuracy that you can achieve with a system like this. I'll also point out, which though it's not as relevant for this work, that we have a suite of imaging package. We have infrared camera, visible, hyperspectral camera that are also providing and collocated information about ocean surface processes, wave kinematics, frontal processes, biochemical processes, et cetera, et cetera. And recently we just added surface velocity measurement capability, but that's not the topic of this though. All right, so the idea is simple. With a MASS, we're able to collect swath of sea surface topography in a given direction. And so what I'm showing here, this is color-coded for height. This is about 6 kilometer swath with a 350 meter wide swath. Sorry. And from this surface map, you can compute a directional wave spectrum. And from the same way explained earlier, you can take this directional spectra azimuthally integrated, and this is what you obtain. This is the omnidirectional spectrum, and we find this this transition, between equilibrium and saturation range, which is really clear, going from a -5/2 power law to a -3 power law. This is consistent with Phillips' 1985 equilibrium model and our understanding of the saturation range, which is great. So we have a lot of data collected over those 3 experiments. So if you take all of them and you fit both equilibrium and saturation range to determine the intersect here for all those different cases, you can start looking at the evolution of this transition wave number as a function of environmental parameter. And you have to recall that Phillips came up with a number for this R number, where he said that R is constant, and came up through his model with this relationship here. And this is effectively what I'm showing here. Here I'm showing a relationship that allows you to parameterize or predict the transition between the equilibrium and saturation range just based on G over U star square, or really just based on U star, which is great. And you can see that there is a very nice collapse of all those data over a broad range of environmental conditions for 3 different experiments, which is quite remarkable. Why do we care? Because again, about the wind wave modeling and upper ocean studies, ultimately a lot of those wave spectrum will turn into a Stokes drift, and you'll compute, like people will compute again for those boundary conditions along with turbulence number from it. So the spectral shape is very, very important. All right, so a little bit of background on Stokes drift. Rotational surface wave have particle orbits that are not closed but are slightly elliptic, and that leads to a drift in the direction of propagation, and that's what we call the Stokes drift. Kenyon came up with a way to compute the Stokes drift based on the directional wave spectrum back in 1969. Here, I'm not going to be focusing on directional spectra. This is a more complicated problem that we're actually actively working on. We're going to start with a simpler approach of just taking the Stokes drift magnitude US of Z just based on the omnidirectional wave spectrum, and you can show that this is how you can compute it. Again, the Stokes drift plays a crucial role in operation dynamics, and that's why we really worry about this. This mixes the upper and ocean and set the boundary condition for couple and RC models. Those estimates of mixing, again, are often parameterized through the Langmuir number, and which is typically used as a ratio of the wind friction, the water friction velocity, to the Stokes drift, and that's why the Stokes drift is really, really important. Using airborne remote sensing observation here, using from the mass, we can start looking at the contribution of those the high frequency component of the spectra to the Stokes drift over a broad range of environmental conditions, and that was really the focus of this work. So the first thing we can look at is a contribution of the equilibrium range to the total Stokes drift, and this is what I'm showing here, the ratio here between the Stokes drift computed in the equilibrium range and the total Stokes drift, for those three experiments as a function of friction velocity u star. As the friction velocity increases, the contribution of the equilibrium range decreases, which makes sense, reaching a plateau for u star larger than 0.35 meters per second. With a value that is quite significant, close to 45 to 65% of the total Stokes drift. So what it really tells you is that you really have to worry about the high frequency component of your spectrum, or your wave spectrum, when you compute Stokes drift, especially surface Stokes drift. So we need to do a better job with this. Another way to look at this is, again, taking those observations that I have, all those spectrum, and recomputing the Stokes drift over a limited range of frequencies, using effectively a cutoff frequency here that I vary from 0.3 to 1.8 Hertz. 1.8 Hertz is roughly what I can resolve with the airborne data. I'm also showing known cutoff frequency from various products. This is ERA 40, ERA 5 is here, ERA 40 here, and cutoff frequency from wave buoys using CDIP, which is a state-of-the-art, great high quality measurement from wave buoys, which has a cutoff frequency of 0.58. So if you look at the contribution of this high frequency component, what you find is that you can get up to an estimation of 35%, for example, for a wave buoy product, because the cutoff frequency is too low. You don't resolve, you need to resolve the higher frequency. This relationship that I'm showing here is actually can be also used to correct surface Stokes drift estimate, computed from spectral limited in situ observation or analysis product, which can be very useful. And again, the paper goes into details about this. All right, so I talked a lot here about the surface, but what about the depths? So as depths increase, the contribution of the shorter wave to the surface is obviously going to be reduced. So that's what I'm showing here. Again, this is similar plot here, but I'm showing different depths. Blue is 0, and this is down to 5 meters. So, and this is in log scale here for clarity of the display. So at 5 meter depths, clearly, there is no contribution from wave with frequency larger than 0.54 Hertz. This is completely negligible here. However, when you get closer to the surface, and I'm putting here again the cutoff frequency of a CDIP buoy, for example, at 5 meters, you're at 7-8% contribution at 0.5 meter water depths from higher frequency waves. So this is not negligible and needs to be taken into account. So how do we solve this? An approach to mitigating this problem has been to use to put a tail on limited bandwidth wave spectra. and that's what I'm showing here. The problem, though, is that if, depending on how you put the tail, if you just patch a tail without considering the presence of an equilibrium to a saturation range, you might get into a trouble. And that's what you're seeing here. Two different cases. One case is where you cut off frequency from your limited bandwidth wave spectra is larger than the transition wave number. So if you patch a tail, you're fine. You clearly, like following the, the expectation of the spectra. The issue arises when your cutoff frequency is lower than your transition wave number. And this is, the case here, where effectively when you patch a tail, k to the minus 3 or f to the minus 5 tail to your spectra, you're going to miss a lot of, you're going to effectively underestimate the Stokes drift significantly. So you have to be careful with the tail. How does it translate with the measurement? Again, I'm taking all my observation, I impose a cutoff frequencies, and that's what I'm showing here. So this is a case, the red correspond to Stokes drift, estimated. So this is estimated Stokes drift on one side, and the Stokes drift measure using the full spectrum. So that's the real Stokes drift, if you'd like, on this end. Gray is the Stokes drift using a tail added, and this is similar to the approach from Berchier. And what you see is when you add a tail, obviously, you do a much better job than with no tail, especially for large US, which correspond to this case over here. On the other hand, for smaller US, where KC is going to be smaller than Kn, then you start getting into trouble, and you have this underestimation of the Stokes drift. So you really have to be paying attention as well to the shape of the tail that you're patching to your limited bandwidth spectra. There is also some issue, and I'll go quickly to this with the parametrization of the transition between saturation and equilibrium range. That makes sense. You have to make sure that this is properly parameterized, or you can lead some significant errors. All right, so why do we worry about this? Again, like, how is that going to translate all those errors into Langley number and mixing? So I'm taking an example here. This is almost a year of data. This is wind speed and computed surface Stokes drift collected from a buoy in the Gulf of Mexico. This is a Luc platform. I just took their product and computed 3 different products. One, where there is no tail added, no correction. This is a product, spectral product provided by NDBC. The red one corresponds to a spectral product where a tail was added. And the blue one corresponds to a spectral product where a tail and a proper transition was also included. And you see significant differences, obviously, between the one without correction and no correction, but also differences when you don't include the transition parameterization. If you take it to the next step, if you look at the Langmuir number, which is the square root of the ratio between the U star as a friction velocity in the water and the Stokes drift, and you look at kind of like the zoom in that I had here, this is what you obtain. And you see and find significant differences found among all those versions, stressing the importance of the parameterization, the fact that you really need a good parameterization of the spectral shape of surface wave to compute Stokes drift. I mean, these are major difference depending on the way the tail is applied to those frequency limited spectra, which is quite remarkable and obviously crucial for coupled RC modeling. All right, so in summary, this is a unique data set of directional measurement of surface wave ranging from kilometer to centimeter scale, and that's using this airborne LiDAR. We have proposed a simple parameterization of the transition from equilibrium to saturation range that can be readily implemented in wave model. This is just function of friction velocity, so this is great, I think. I've looked into error analysis. to the estimated Stokes drift based on those spectra, looking at different cutoff frequencies and transition wave number, as well as the impact of the misrepresentation of the transition from equilibrium to saturation range. And I want to stress again that by improving estimate of the Stokes drift, and hence better estimate of the turbulent long mean number to be used in this coupled model, the sensitivity of this number to be spectrally to the spectral estimate of the Stokes drift is demonstrated in here. This is really important. What we have been working on now with Nick is the directionality of the wave field. This is important, especially for the the spectral shape. We know that we have a bimodal shape for the directional spectra, and it will have an impact on those estimates. We know that omnidirectional spectra overestimate the drift. So this is some work that we're actually working on, really expanding those results to directional property. On this, thank you.